You know those problems where there are just so many possible solutions you don't even know where to start? We're always trying to find the single best one, the cheapest, the fastest, you name it. Well, today we're going to break down a really powerful algorithm that's built to do exactly that.
Seriously, think about it. When you're trying to book a flight or your map app finds a route, it feels almost instant, right? But behind the scenes, there are literally millions, maybe even billions of possible paths it could take. If it had to check every single one, you'd be waiting forever. So how on earth do they find the perfect one so fast? That's the exact puzzle we're going to solve today.
So here's the game plan. First, we'll talk about why we even need a smart strategy like this. Then, we'll introduce the star of our show, Branch and Bound. We'll walk through a journey step by step, see its cleverest trick in action, and finally, watch as it zeroes in on the perfect solution.
Okay, first stop, understanding the sheer scale of the problem. When we're hunting for that optimal solution, we're usually facing a gigantic number of possibilities. Now, the simplest approach is just to check every single option, one by one. We call that a brute force search, and as you're about to see, for most interesting problems, it's just a total non-starter.
It's kind of like being dropped into a massive maze. Sure, you could try every single path until you eventually stumble out, but think of all the time you'd waste hitting dead ends over and over. What you really need is a map, a smarter way to navigate. You need an algorithm.
And that brings us to our strategy, the branch and bound algorithm. And honestly, the name itself is the perfect clue to how it works. It really just comes down to two simple but incredibly powerful ideas.
So what really makes this algorithm so special? Well, it's not just wandering blindly through that maze. Instead, it's actively building a map as it goes, a tree of all the possible paths. But the real genius, the secret sauce, is that it knows which parts of that map it can just cross off and completely ignore, which saves a massive amount of work.
So let's just break down that name. Branching is all about exploration. We start at the beginning and we branch out, creating this tree of choices. And the key rule is to always follow the path that seems cheapest so far. Then there's bounding. This is the efficiency trick. As soon as we find any path to the finish line, its total cost becomes our upper bound. And from then on, we can use that bound to prune or just chop off any other path that's already more expensive. I mean, why waste time exploring a path that's already guaranteed to be worse?
All right, theory is great, but let's actually see this thing in action. We're going on a little quest to find the absolute cheapest path from a start point, S, to a goal, G. Every line you see here has a number, and that's the cost to travel along it. So we kick things off right at the start, S, where our cost is 0. From S, we have two choices. We can go to node A for a cost of 3, or we can go to node B for a cost of 6. Now, this algorithm is an optimist. It always checks out the cheapest-looking path first, so it makes its choice. Let's explore the path to A.
And this is that core branching rule in action. We've got two active paths we're thinking about, the one to A and the one to B, and we just pick the cheapest one to continue from. Since the path to A costs 3 and the path to B costs 6, A is the clear winner. So let's see where that takes us.
Okay, so now we're at node A, and we can branch out again. If we go to node C, that adds a cost of 7 to the 3 it already took to get here, for a total of 10. Going to D adds 2 for a total of 5. And hey, we could even go back to S, which adds 3 for a total of 6. So now we've got a whole new list of paths to think about.
And this is where things get really cool. Let's look at all our options. We have the path to C at a cost of 10, the path back to S at 6, the original path to B also at 6, and the path to D, which is only 5. Since 5 is the lowest number on the board, the algorithm decides to explore from D. And this is where the bound part of the name really starts to shine.
So we've zeroed in on our most promising lead. The path through D seems like our best bet right now. And from D, we see a path that takes us right to our goal, G, for an extra cost of 4. This is a huge breakthrough.
And boom, there it is. We found our first complete path all the way from start to goal. The total cost? 9. This moment is absolutely crucial. That number, 9, becomes our very first upper bound. We now know for a fact that it's possible to solve this for a cost of 9. So any other path that costs more than that, we can just ignore.
So let's look at all those other partial paths we were keeping on the back burner. We've got paths with costs of 6, 7, 8, and even one that's already at 10. Before we found our solution, any one of these could have been the winner, but not anymore.
With our new bound of 9, we can do some house cleaning. Take a look at that path through C. It already costs 10. Well, since 10 is already bigger than our solution of 9, there is no way on earth that path will ever be better. So we prune it. We just get rid of it. That is the magic of the bound. It saves us from ever having to explore that entire branch of possibilities. But hold on, we're not done yet. Finding a solution is great, but our mission is to find the optimal one. We found a path that costs 9, but could there be an even cheaper one hiding in the paths we haven't pruned yet? Let's find out.
So the algorithm goes back to its list of active paths and, you guessed it, picks the next cheapest one to explore. After checking the paths that cost 6 and seeing they don't pan out, the next cheapest one is the path through E with a current cost of 7. And what do you know? From E, there's a direct shot to our goal, G, and it only costs 1 more.
And that is a new record. We found a better solution. The total cost is 7 plus that final one, which equals 8. That's cheaper than our last solution of 9. So 8 becomes our new, much tighter bound. We've just made our search even smarter.
And this new tighter bound lets us be even more aggressive. Any path in our list that already costs more than 8 can be pruned immediately. In fact, even a path that costs exactly 8, like the one through B, can be thrown out because we know any extra step will make it more expensive. We get to ignore even more of the maze.
So at this point, if we check our list, none of the remaining paths can possibly beat a cost of 8. The algorithm confirms this, and once every path has either been fully explored or pruned, it stops. And this is it. We've found it. The guaranteed cheapest path from S to G has a total cost of 8.
So the big idea here is this. Branch and bound isn't just searching blindly. It's actually learning as it goes. Every time it finds a solution, it gets smarter, allowing it to focus only on the paths that still have a real shot at being the champion. It's this beautiful mix of being optimistic, but also ruthlessly efficient.
And this core logic of branching out but setting strict bounds to stay efficient, it's everywhere. It's used in logistics, in scheduling factory floors, in AI that plays games, even in complex scientific problems. So the next time your GPS spits out a route in 2 seconds, you'll know why. It's not checking every single street in your city, it's intelligently pruning the impossible ones. It makes you wonder, what other huge problems could we solve if we just found the right way to prune the search?